24% atoms, 4.6%. Then you take the atoms, and in the warm, hot intergalactic medium from 100,000 Kelvin to 100 million Kelvin, this is this fraction, basically, of all the atoms. They are very, very ionized. So you have protons, you have electrons, and all the metals, the heavier elements are ionized. And now you're left with the galaxies, which are 7%. And they consist of 90% ionized hydrogen, boring, 10% stars, everything is ionized inside the stars, and you have planets, no? Okay, it's a little fraction. So most of the universe is really highly ionized. And we love the highly charged ions because they are not only natural and ubiquitous, but they allow us to investigate scaling laws of fundamental interactions, which grow very rapidly with the atomic number C. So the binding energy, everyone knows it, C squared. It will bring from hydrogen to hydrogenic uranium the binding energy from 10 eV to 140 kiloelectronvolts. But much steeper dependencies is given by the relativistic fine structure, which grows with the fourth power of C, or the quantum electrodynamic contributions. And they grow from microelectronvolts to the range of kiloelectronvolts, at least for the relativistic contributions, and half a kiloelectronvolt for the QED transitions. And there are further effects like the hyperfine structure effects, nuclear size effects, and the transition probabilities of forbidden lines, which grow with the 10th power of C, some of them. So it's very interesting. It also gives you the opportunity to take an element, change the charge state, and by doing so, you are tuning the relative strengths of the interactions. So you change the ratio of correlation to some other effect of interest. That gives you many more opportunities for systematic studies, only if you are able to produce and investigate the highly charged ions. And for that, there is a very nice laboratory tool, which you all know, which is the electron beam ion trap. In the electron beam ion trap, you have a strongly focused electron beam, strongly focused by a magnetic field. This beam has a fraction of an amp, several tens of milliamps, hundreds of milliamps, and it produces a negative space charge. This negative space charge is capable of attracting positive ions. Not only that, but the negative current ionizes anything you throw into the system, and therefore you produce the ions, ionize them, trap them, and excite them with this electron beam. And classical electron beam ion traps have been used for a lot of studies with X-ray spectroscopy, because the natural energy scale of highly charged ions are X-ray transitions due to this scaling. So you have your electron beam, the electron beam is accelerated to the suitable energy for the production of ions. Atoms are sent in as an atomic or molecular beam into the system. They are ionized, they're trapped, and you have some X-ray detector, spectrometer, or whatever, and investigate the electronic transitions of those ions. So you can put here any type of spectrometer, and people have done that. This was pioneered in Livermore, and it's a very nice tool. You can decide the charge state of the ion by choosing the electron beam energy. And also by choosing the electron beam energy, you can resonantly tune into transitions of interest. This is, for instance, a view taken with a commercial reflex camera, 1 minute exposure time of iron 13 plus, trapped in the EBIT. So this is 5 centimeters, and you can see here the green coronal line we saw before in the sun. And we were interested in these transitions for several reasons. They had not been really investigated in detail, exception made of the astrophysical observations. And then we started installing a visible spectrometer with gratings and collecting the light and analyzing the spectra emitted. Here you see a transition split in the 8 Tesla magnetic field in the several Zeeman components. And these are interesting, but we always have the same problem in an EBIT. The trapping potential is very, very deep. We have kiloelectronvolts trapping potential, the effective trapping potential, given by the product of the space charge of the electron beam and the charge of the ion which you are trapping in. A very deep trap means a very high temperature. So if you are trapping with kiloelectronvolts, your temperature will be fractions of kiloelectronvolts. And that's the problem. All these transitions, even when we investigate them with lasers, by shining in lasers into the EBIT and collecting the fluorescence, are much broader than anything you are used to in laser spectroscopy, meaning all our efforts to cool down the ions by evaporative cooling brought us from the many megakelvin range into the hundreds of kilokelvin range. It's not good for laser spectroscopy. However, we will be interested in investigating with lasers the properties of ions. And we did a bunch of studies, not only in the visible range, but also utilizing synchrotron radiation, free electron lasers in the range of 800 eV, and synchrotron radiation from 6 kiloelectron volts, 13 kiloelectron volts, always exciting resonantly the ions which had been produced by the electron beam and trapped and collecting the fluorescence by suitable detectors. Still, we were fighting with the temperature, so the idea is we have to do something against it. And the highly charged ions would provide us very interesting transitions. The transitions in the visible range would have a very low sensitivity to disturbances, perturbations due to DC and AC stack shifts. They will provide an excellent frequency stability, and they will be suitable as frequency standards. And since the whole fine structure splitting we are talking about is dominated by the Coulomb field, the external perturbations won't play a role. And there is a number of optical transitions which could be investigated from beryllium, boron-like, hydrogenic, and even the most interesting one, the hyperfine splitting of the hydrogenic ions. So, to cool them, you cannot use lasers because you would need an X-ray laser. So what we did is we thought using a crystal of Coulomb laser-cooled ions and putting a highly charged ion there would allow us to sympathetically cool them. This idea was not new. We just wanted to realize it. And again, this realization would bring us from the megakelvin into the below Kelvin range, reduce the Doppler width, and allow investigations at low polarizability. So, a very interesting subject which arose recently was the issue of searching for time variation of fundamental constants, specifically of the fine structure constant alpha. But this cooling should be also applicable to X-ray laser spectroscopy. I mentioned people have tried before and to sympathetically cool highly charged ions in Livermore, but we were interested in going farther than that. So we developed a cryogenic linear radio frequency pole trap, where the guts of the system are kept at 4 Kelvin, and this was basically a standard radio frequency trap with all the cryogenic environment, which will give us a very, very good vacuum. And this very good vacuum of 10 to minus 50 millibar will be sufficient to hold highly charged ions for long times. It will also, the trap needed a lot of access ports. Contrary to many other traps, we need 16 access ports, we need external ions, we need imaging. This is common, having imaging, having lasers, but we have to inject ions and atoms. And reducing the black body radiation was beneficial for other reasons as well. So we built that thing in Heidelberg, and we brought it to Aarhus, because in Aarhus, the group of Michael Drefsen was very experienced in using radio frequency traps, and they work with molecular ions. And during the commissioning time of 1 year, Oscar Versolato and a bunch of students of Michael and of our group did great work measuring different things. The basic idea was cooling the molecular ions once by the virtue of the cold environment, which means you are not heating them rotationally or vibrationally because the infrared radiation of the environment is suppressed, and additionally applying some clever laser cooling schemes which have been developed by Michael Drefsen in his group. So you have here a Coulomb crystal of magnesium plus, and you add magnesium hydride plus, which is formed by a chemical reaction within the trap. And the cooling lasers are applied to the magnesium plus. It delivers a very cold Coulomb crystal, and this very cold Coulomb crystal has on its surface magnesium hydride ions. These magnesium hydride ions are cooled now by a combination of methods. The most important, the key element here is things slowly go down from the vibrational state into the raw vibrational ground state, but very slowly. And here there is a bottleneck, and in this bottleneck, which is extremely slow, you apply a quantum cascade laser to accelerate this decay. And with that, it was possible to quickly reach a very low raw vibrational distribution of states in this molecular ion. Okay. And then you measure the raw vibrational distribution of the molecular ions by firing a laser which dissociates with sensitivity to the rotational state distribution the ions, the magnesium hydrides. And by looking at the size of the crystal, you can determine how many have been destroyed, and therefore you can determine the rotational state distribution. Okay, so that's done in this way. Here you have outside the magnesium hydride, then you fire your laser, the crystal size changes, the crystal shrinks in one dimension, the magnesium stays in the center, the magnesium hydride is outside, and by firing several shots, you can figure out what was your rotational state distribution. And what it was found at the same time is that very, very minute amounts of helium gas introduced into the system were also as efficient or even more efficient than the laser scheme for cooling the ions. And the reason for that was the collisions with the 5 orders of magnitude lower pressure buffer gas than usually were sufficient to cool the rotation of the molecules, because the vibrations and the translational degrees of freedom had been already cooled by the interaction with the Coulomb crystal. So the rotational cooling was only necessary for these little degrees of freedom, and the helium buffer gas at pressures of 10 to the 10th per cubic centimeter was sufficient to achieve that. Okay, and there were a lot of measurements on the rotational state distribution, and it showed that this method was efficient. At the same time, it was also possible to manipulate the micromotion of the ions in the trap, and by letting them have a micromotion which was larger than usual, the collisions with this helium buffer gas would allow you to manipulate the temperature distribution and the quantum state distribution. One can say at this moment the final analysis of the second set of data is not finished, but you can bring 98% or 99% in the raw vibrational ground state. And Oscar Versolato did also great measurements on very, very slow infrared transitions. For instance, this one at 6 Hertz decay rate, only influenced by other transitions with 0.1 to 1 Hertz, coupling these rotational states. So it was possible to measure that because the trap had extremely long trapping times, very little interactions with the environment, and the possibility to prepare very pure quantum states. Now we brought this machine after 1 year back to Heidelberg to its original purpose. And there we used beryllium ions cooled with a laser of appropriate wavelength, and then we inject here highly charged ions. And at the beginning, we played a little bit. This is the work of Lisa Smerger and Oscar Versolato with different configurations of the ions. And what you need for this game is you need an electron beam ion trap to produce the ions. You have to transfer the ions, decelerate them, and bring them into the cryptics. And this thing has to be done in several steps. The first thing is you take the ions, you bend them into this beamline. Here you apply a pulse which is capable of bunching and slowing down the state, the highly charged ions, and then you bring it into the Paul trap. Into the Paul trap there is a potential against they have to fight to go up, and once they are there, here in the Paul trap, it's represented here, you close the trap and let the highly charged ions ping pong back and forth many times. And in this ping pong, what they do is they cross the ion crystal of beryllium plus, which has been prepared in the trap. And by doing so, they lose more and more energy, and finally they get stuck in the ion crystal. And this getting stuck is what you want. Because it means they are crystallized within the crystal, and you can prepare now different configurations. Here you have a very large beryllium ion cloud. It's liquid, and you see 20 argon-13 plus ions which are just building a tunnel. Here you have a mixed phase crystal with only 3 argon-13 plus ions. You have here a very nice crystal with looking like an eye, where the argon-13 plus sits in the center and pushes out the beryllium plus sympathetically cooling ions. So now you image this system, and by imaging the system, you can realize what is the charge state of the ion and even what is the temperature of the ion there. And the separation of the cooling ions from the highly charged ions is obviously a function of the repulsive potential in a linear string given by the highly charged ions. So there is the image analysis for that. You can cool the highly charged ion with a single beryllium plus ion. This is very nice because that would allow us in future to carry out measurements where you entangle the quantum state of the two ions and ask the beryllium cooling ion, what is the quantum state of the guy there? If the guy moves from here to there, you see the center of mass changes, and if you finally lose the highly charged ion after 20 minutes, trapping time, you are left only with a beryllium plus ion. So, and these movies perhaps would work. This shows a configuration of ions jumping from one side to the other. There is, and the highly charged ion is somewhere there. And you know, analyzing the configurations, you gain the certainty of what the ion you have there. We were interested in these highly charged ions for a very long time because the hyperfine transitions in the hydrogenic ions are very sensitive to fundamental interactions. And the Bright-Rosenthal effect, the nuclear charge distribution, the nuclear magnetization distribution, the QED effects. This is very, very interesting, and these are optical transitions. And Stefan Schiller proposed, we have carried out some measurements in Livermore of these hydrogenic transitions in the visible range, and Stefan Schiller proposed, why doesn't one use the highly charged ions in pole traps? Because they would be extremely good for fundamental tests, for tests of the time independence of fundamental constants. And he calculated in a hydrogenic approximation what will be the sensitivity to external these perturbations. And you see all these sensitivities are extremely small. And recently, several groups of theoreticians, Victor Flambaum, Julian Berengut are among us in the conference. You can ask them. They have produced a very large number of interesting papers where optical clocks and highly charged ions in optical clocks have been proposed as very sensitive probes of changes in fundamental interactions. Yeah. The idea is you have some optical transition in highly charged ions, and you can even choose and tailor the optical transition to be insensitive against quadrupolar effects, which are a permanent nuisance in this business. Now you produce highly charged ions. This is iridium. It was the ion which was supposedly to be the best one for investigating the time variation of fundamental constants. And this iridium 17 plus was completely unknown, so we changed the electron beam energy. We produced spectra of different unknown iridium 17 species. You see here the spectral range in nanometers, and here the acceleration potential. And these letters here tell us an unknown charge state. Finally, this guy was identified as the iridium 17 plus, and then we started looking at the optical transitions in iridium 17 plus. They arise from a level crossing where the 4F14, 4F13, 5s, and 4F12, 5s square cross. And there have you a multitude of optical transitions. Some of them are interconfiguration transitions, and they are particularly interesting for this business of fundamental constants. They have a very much larger sensitivity to a change of alpha because of the relativistic effects, which is where alpha sits. And the level scheme was completely unknown, so Alexander Windberger had to make a tremendous business of comparing platinum, iridium, osmium, uranium, and tungsten in various charge states, measure all the optical transitions, try to figure out who is who, look at scalings which were easily predictable by theory, whereas the absolute numbers were not so easy to predict. And finally, he managed to identify the lines. The identification was confirmed by looking at the G factors, the Zeeman splitting of the different transitions. And with that, we were sure about iridium 17 plus. Then you could carry out a comparison with various theories. This is Fock space coupled cluster calculations, configuration interaction, Dirac-Fock term, Cowan code, flexible atomic code, configuration interaction, and this is the experiment. And you see here we have a very nice agreement which is nearly able to allow us for direct identification of the transitions. But as I mentioned before, first we didn't know who is right here. So we have to do the whole business. Now, this system of M1 transitions, which was analyzed here, allowed us to fill by Rydberg combinations some of the gaps. And these gaps contained, among other things, E1 transitions, which are between 4F13th and 12, yeah? And these are very, very forbidden. There is configuration mixing, and it induces a little bit of E1 transition. They have a few hertz transition rate, and they are extremely weak. But we could first identify them, and then we could look more carefully and find them. And we were left a few months ago with this uncertainty. It could be like this, or it could be like this. If this E1 transition is assigned the other way around, the extremely sensitive transition for alpha in time variation studies will be this, otherwise it will be that one. And it seems now, because we have been continuing those measurements, this is a typical spectrum, this is not yet published, that we are sure that the M2E2 transition is at 267 nanometers, and it agrees with Chuba's calculation. But again, this is not yet published. The other work was published by Winberger et al. So we are happy with that. And there is another number of other transitions which have been proposed. I have borrowed from Mariana Safronova some interesting elements. For instance, neodymium 13+, which will be silver-like. Here you have this state which lives for 15 days. Okay, that's nice. No? And it has a large sensitivity to alpha variation via this parameter Q. It's an E3 transition. Yeah? But you know, you can go to praseodymium 10+, and then you have here 1 day. Oh, it's okay. It's even better. And if you go to 9+ with 4 valence electrons tin-like, this transition will have 20 million years lifetime. It's an M3. It's very good. It's an optical transition, extremely narrow, very appropriate for clocks. I like this very much. The only problem is that your student preparing the transition would have to have been living 20 million years ago, sometime in the late tertiary. And this is nothing you would wish, because at that time life was dangerous. So let me summarize. We have been building a cryogenic radio frequency trap, which was ideally suited for cooling highly charged ions and molecular ions. We can prepare now molecular ions in the raw vibrational ground state quite independently of the molecular species we are talking about, because we do not need a specific laser for the molecular species. We need only a laser for the sympathetically cooling ion. For the highly charged ions, we have been able to remove a major inconvenience, which was the high temperature in the megakelvin or hundreds of kilokelvin range, which we had. That gives us the possibility to investigate highly charged ions in a laser environment. We did that by implanting the highly charged ions in Coulomb crystals, and that has lowered the temperature to our upper estimate now is 200 millikelvin. It will open us and other groups opportunities for optical clocks and fundamental studies, which are the result of fundamental insensitivity to perturbation. This work has been carried out basically by Lisa Smöger, a PhD student, Oscar Vesolato, a postdoc in my group, now Maria Svatz, who built the cryogenic Pole trap. The measurements in the optical range have been carried out by Alexander Windberger and Henrik Becker. We collaborate with Pete Smith in all this business because of the cooling lasers, because of the later application of quantum logic at PTB, and we have had a very good time with Michael Drevsing learning things about the cooling of ions in sympathetic crystals. And these are the guys responsible: Lisa, Maria, Oscar, Henrik, Alex, myself. Here you see Michael and Pete, and this guy you should know, and thank you very much.